was thinking, I was preparing something else, but then I don't think I can finish that. Since I never talk about TCQ, then I guess I can talk about TCQ. It's Trellis code quantization. So basically, the problem is following. We have, let's say, have a source here, which is IID source, and then let's say this is like some kind of discrete time continuous source. Discrete time continuous. So then we have like, let's say something like x1, x2, and so on. Actually, it doesn't necessarily be IID, it doesn't matter. But let's say we want to transmit this source, then we need to kind of quantize it. Right? We need to quantize it. And the simplest quantization is just do a scalar quantization. And let's say uniformly quantize it. So let's say if this is like a Gaussian source, have let's say variance 1, like 0 mean, then maybe you know that the source have PDF more or less like that, and maybe around Z, the tail will die down, and you probably won't see it anymore. Then maybe you can just kind of build a uniform quantizer, let's say, from -v to v. Let's say you can split into 8 pieces uniformly, and then if this one is not exactly 8, but it's kind of then like that. Then maybe if you have the sources here, something like if you appear here, then you will just quantize to this interval here. So each interval will be represented by an index, right? So you can represent by 3 bits here, because you have like 8 intervals here. So this is very simple. It's just a uniform quantizer. Actually, also 1D also. Now, but if you think of that, this is very inefficient, because let's say let me step back about compression. Let's forget about compression. Let's say I just try to send these indices through a channel. So after compression, after quantization, I will send this. So what I mean is very inefficient, because if you think of that, if you pair up each of these x1, x2, let's say, if you draw it out, what does it look like in 2 dimensions? You will have the distribution profile will be more or less also a Gaussian or something like that, right? So what I mean is that you have this maybe probability point 1 will be within this region, let's say, point 2 within this region or something like that. What I mean is you will see the x1, x2, or each pair of x will be appear like something like that, right? Kind of like circular in a sense. Then what's the quantizer like in this 2D here? You basically, for this one, if you extend this to 2D, you will just have the quantization region will be something like, okay, again, this is like 4 for each, like 8 intervals for each dimension. So therefore, you have 64 regions, right? Something like that. Blah, blah, blah. What happens is this region is just totally wasted, right? Because you have like indexes trying to represent this region here, but basically you will left almost very unlikely to have your x fall into this region here. So therefore you see that it's very wasteful actually. And of course I can look into higher dimensions even. So if I look at like 3 dimensions, I have a sphere, and I guess I even have like more indices are wasted. If you look at higher and higher dimensions, actually, you have lots of waste here. And of course, like one thing you can do is like here is like quantization here, and let's say I can first do a compression here, like entropy coding, basically, just maybe entropy coding and encoding, let's say. So this encoding is just here, something, let's say. You can think of it just as here. And then like you pass through a channel that is lossless, and then you kind of decode this, and then you dequantize it, and get back your source here, let's say x hat here. And okay, if you add this, what I just mentioned is like without this entropy coding step. So if I do entropy coding, what does that mean? Actually, what it means is basically I will depends on the probability of each of these indices. If these indices are less likely to happen, I'll give it a longer code length to represent it, basically a longer code word to represent that region. And if this here is more likely to happen, I will have a shorter code word. So you can think of this Zip or Hoffman coding, right? So then in a sense, you get, okay, you solve partially the problem I just mentioned. Actually, you solve most of the problem I just mentioned. You basically, because this is very unlikely to happen, now you will use a very long code word, and and as a trade-off, you can have much shorter code word for region, like for X when it lies in region here. I guess I'm a little bit not making myself very clear. One thing is like, without the compression, what happened? Without the compression here, let's say I have 64 indices here, right? So I need to use 6 bits. So each of this region here, when the X lies in each of this region here, all of them will use 6 bits to represent this region. For example, this can be called, let's say this S start from 0, 0, 0, 0, 0, 1, and so on up to this is 1, 1, 1 here. This S is also 0, 0, 0, up to like 1, 1, 1 here. So for example, this one will be basically 1, 1, 1, 1, 1, 1, right? And this one will be like, or like this one will be like 0, 1, 1, 0, 1, 1. This one, because this is 0, 1, 1 and this is 0, 1, 1 also. But what I'm saying, like, it's very inefficient because I know this is very unlikely to happen, but this happens all the time, right? I can trade it off. If I use Hoffman or like any other entropy coding scheme, what happens is like I can change the code length of these indices. Now I will use a shorter code length for this index and use a longer one this here. So I may have a much longer code length here, let's say 1, 1, 1, 1, 1, 1, 1, 1, 1, I don't know what's that, but this may be just 3 bits, let's say. Then therefore you will have gain there. But okay, this solves the boundary problem I just mentioned, but there's still problem here. There's still inefficiency with the so-called, they call it granular gain. So actually, I'm not sure I should start with this granular. But what I want to say is, it still have inefficiency in the sense if you think of like, now in this 2D I'm only going to put this region like this way, in this regular sense, rectangular sense, or something like that. And if you think of that, I can get less number of code to send if I can find a shape of this region that have the same area, but you kind of pack it in a better way. Let me give an example to make it clear. So let's say for this same thing here, if I use, because I know that eventually what's the mean square error during, or this dequantization error here. The dequantization error will basically kind of this error, let's say, what symbol should I use? Dequantization error will be kind of proportional to, in terms of mean square error, will be kind of proportional to the size of the region. This is very rough. I mean, I shouldn't say proportional. I'll just write like that. So, in the sense that if this region is smaller, then you expect the quantization error will be smaller, right? And if it's bigger, it will be bigger. And what I want to say is like, if I can find another region have the same area, but if impact it more nicely, then I can increase, I can reduce the number of covert to sand. Yeah, but still with the same quantization error, right? So one example in 2D would be something like that. I can pack, instead of using this square here, I can pack with hexagonal. So if I pack with hexagonal, basically, I can pack with the same area, like this have the same area as this, but you can kind of argue yourself that you can pack more nicely. Let's see, how can I argue myself? Okay, let me try to argue myself next time. I don't know. But let me just take my word for now. So I pack better here than this one here, in the sense that I will have a actually I didn't say it correctly here, because it's not exactly proportional to the size of the region, but it's actually proportional to something like that. Let's think of it this way. So what's the mean square error here? For example, if you have a, let's say, different region here, let's say the x appear like half uniformly here, let's say. Then remember what do you dequantize to? When you dequantize, you only know that like your x is lies into somewhere here, right? Then the best thing I can say is like I will just say, okay, if you give me, if you tell me x is inside this region, I'll just say that like, let's say x is just the estimated x will be just at the middle, right? Middle of the region. Something like that. Right? So now if you think of the mean square error sense that, so if I have, of course if the error is the same, okay, I didn't say it correct, I totally messed up. I mean, if the area is the same here as here, of course the number of covert, the number of the space they can cover will be the same, right? The size is the same. So then the number of coverts won't decrease, we'll have same number of coverts, but the mean square error will be smaller. Because if I use this one, again, like if I have a polynomizing here, then it will dequantize to something in the middle, right? And now if you think of that, if this area is equal to this area, you can argue that if your shape is more spherical, it's more like a sphere, your mean square error should be smaller. Because you think of that, like what's the mean square error really do? You're assuming in this region here, like x is kind of uniformly appearing. And remember, the mean square is kind of like you take the square somewhere and then sum over there and take the average. So actually, the most of the contribution of the mean square error will be from points that is kind of far away from the middle. So if you have a shape it's like that, it will be very bad. Because even your area is the same as here, this will give you a very bad mean square error, and this contributes to a very bad mean square error to your final mean square error. Like very bad error to your final mean square error. So therefore, the more spherical your region is, then you will get a better gain, like better mean square error. So therefore, like intuitively, this one will be better than this one. And that's exactly like, of course, like this is just 2D. You can go higher dimensions, and you can make a shape like more and more like spherical to pack the space there, and then you can get more and more gain. So, but the gain here is like they call it a granular gain. It's like, or like you can think of like a packing gain. So, how you put this code here. So, but the problem is, of course, I can, let's say, group several of this input each time. Let's say here I just do 2D, I can group like 4 at a time, 5 at a time, and just build a high dimensional lattice with a complicated region that is very much like a sphere. But the problem is it's very hard to decode because now you have like, let's say 10 dimensions, and you need to decide like in this 10 dimensional space, any point that you have, which is the closest, or like which region is actually that point lying to. And in general, that is basically a very difficult problem. So therefore, like what we talk about here, this TCQ is a practical way to kind of like emulate this thing here, to try to build a support region, or not support region, the cell of each of these code to be more spherical. So I haven't started anything about TCQ yet, but this is the kind of idea why. So let's see. Okay, why Trellis coded? So actually it's closely related. Actually, it has a dual to the so-called Trellis coded modulation in communications. In the sense, like I want to transmit let's say transmit some bits over a channel, and I need to protect those bits because the channel is lossy. And I can use this TCM to kind of like protect it. And let me maybe give a quick introduction of this TCM. Okay. So basically we have a dual problem. It's just we have some source. Let's say I have some bits here, B1, B2 that way. And then I need to transmit it through a, so I have an encoder here. So anyway, I kind of a modulation. Let's say I have an X1, X2, something like that. And then I go to a channel, and I receive X1, X2 hat. So this is a channel. Then I decode it. I get back this B1, B2. So hopefully this B1 should be the same as this B1 here. So even this channel is lost here, I should be able to kind of like fix the error. So, okay, TCM is basically based on convolutional code. So a classic example of a convolutional code is I have something like this. This is 2D element here. Now, so I have these streams coming in, B1, B2, so on B3, blah, blah, blah. Oh, by the way, of course, like, the way I'm able to kind of mitigate, okay, no, but to correct these errors is because I introduce redundancy to my input here. So I expect this x1, x2 actually is redundant. I have redundancy there, and using this redundancy, I'm able to correct any errors that are introduced by the channel. So here is the redundancy I'm going to get. So actually this will be the x1, x2, something like that. So basically, for each bit coming in, I will generate 2 bits. So this is a weight, so-called weight 1/2 code. So I double, kind of like introduce the same amount of redundancy as the incoming source. So if you look at this, what does that mean here? Like maybe I should put a draw it like this would be better. So add here, and then output here. That's it. So this is add here. So basically everything is binary, so it's just bitwise addition. So for example, if I have a 1101, let's say, so this is just a delay element. So and you can think of like at the beginning, this delay element have stored the stages 0, 0. So at the beginning is 0, 0. So when you have an input like that, then you have 1, 0, 0 here, right? So then you get like 1, 0 here, let's say.
What is the D?
Say that again?
What is the D?
D is basically delay. Or you can think of C inverse. Yeah, C inverse. So let me draw it like this, x1. So x1, x2, x3, something like that. So then the first one will be 1, 0, 0. I get 1, 1, let's say. And then in the next time step, then this 1 will get into here. Now you have 1, 0 here, you have 1 here. And then you will have this is equal to 0, 1, because this is 1 and this 0 here. So in the next time step, I keep moving, this will be out, and I have 1, 1, 0 here. So I will have like 1, 0, 1, 1 is 0, 1 here. And so on and so forth. So you see this convolutional code. So at least you know how the encoding works. So now I won't send this. So we call it modulation because typically we won't send this 101 or something like that. Typically we'll be sending the signal. Right? The signal will be kind of whether you are have that kind of modulation that have a cosine and sine component, add them together, or like if you just think of a very simple, like two-dimensional space, you can think of like what I'm going to send will be something like let's say this is 0, 0. Let's say this is 0, 1, or like this is 1, 0, and then or 1, 1. 1 here. So when you have a 1, 1 here, we'll send this thing. When we say send this thing, it's like the signal representing this thing here. And then like if I have a 0, 1, I will calculate some this thing and so on. So and then like at the decoder, you will, of course you send the signal, have this complicated modulation, I forgot. And at the decoder, you try to demodulate that, essentially you will basically receive another point somewhere in space, right? And based on that point, you will, if I receive here, so if I don't have redundancy, what I would say, I would just say, it's likely to be CO1, right? So I would just say, it should be CO1. But I should take advantage the fact that there's some correlation in the sense like, you see like, what we're transmitting here is not memoryless anymore, we introduce memory here. So we can use the labeling information to take advantage of that. So I can, because of the last one I received is 0, 0 instead of 1, 0, it can affect my decision whether I should consider this is really CO1 or something else. So it will become clear as I give an example again. So let's say in this example here, the first x1 I said will be 1, 1 here. Right? I said x1 here, and then I think x2 is CO1 is here, and then x3 will send CO1 again is here. So, and I can have some error. X1 can be not here, but maybe go to here, become x1 hat here. Or maybe x2, x3 is more or less nearby, x2 hat is here, x3 hat is here. Let's say. And then what I can say is like, based on x1 is here, I can say what's the probability of x1 being here, 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 here. Right? And similarly, I can say what's the probability of x2 being here, 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 here. Something like that. So before I go to that, let's say why we call this Trellis thing. So the Trellis, because like if we draw this convolution code, we can kind of like elaborate that into a Trellis diagram. So in the sense like I can represent this whole thing in a Trellis form. Basically, I can consider like these are the different states that can happen in the system, this encoder. I can have like 0, 0, I can have 0, 1, I can have 1, 0, I can have 1, 1 here, right? This is a possibility. So you think of this as time here now. So at times instance equal to 0, I'm in this here. My state is 0, 0 here. Now what can happen in the next time instant? Again, I can have this different states here. So it depends on my input, right? So if I start with 0, 0, if my input is 0, then I will still in state 0, right? But if my input is 1, then I will go to state 1, 0, right? So there's a draw 0 here, draw 1 here, right? Because now I move this 1, like this 0 is gone, and the 1 moved to this. Right? So, and then similarly, 0, 1, if I get 0, I will go to 0, 0, and then if I get 1, I will get 1, 0 here. Yes. And then if 1, 0, I get 0, I will go to here. If I get 1, I'll go to here. 1, 1, if I get 1 plus 0, I will go to here. If I got 1, I'll go to here. And this is time equal to 1, let's say. And I can keep repeating this trellis. And of course, like, you know that like, if this is 0, then what should be transmitting? I should transmit transmit what?
0.
Yes, 0, 0 again.
Yeah.
And this is like, I guess you can feel the words basically. If I have 1 here, I have 1, 0, 0, I should be transmitting like something like 1, 1 there.
Yeah.
Yeah, I have 1, 0, 0. And so on and so forth. So this I know that I will be transmitting this. So now if I think of like, okay, this is the encoder wheel, but I can use it for the decoder also. I mean, I'm talking about encoder, but I can, I mean, when I decode, I can use the same thing trying to figure out what's going on. So what I mean is like, if I So as I said, I can repeat this Trellis thing, like I can repeat that. That's the same thing here. Something like that. And so on and so forth. My point is that like you see the correlation now. It's not that like you can go through any path. There's some constraint on like what output you can be like at. For example, you can only go like this way and then this way and so on, but you cannot go this way and suddenly jump to this step here. So that means that if I send 1, 1 afterward, then I cannot send, I don't know what it is, but this thing I think is only 0, 1 or 1, 0. So after you transmit 1, 1, you can only send, you expect that like it cannot be 1, 1 again, it can only be 0, 1 or 1, 0. Let me put this, like 0, 1 is it. 1, 1, 0 basically is 1, 1, 0. No. This is 0. 0, 1, 0 is 0, where is it?
1.
Maybe I'm wrong about what I said. Let's see. 0, if I have a 0 here, there is 1, 0, 1, 0. Yeah, okay, I guess I said something wrong. This is 1 and 1. Wait a second. 1, 1, 0. 0, yeah, that's a 0, 1. Oh, this is 1, 0. Okay, that's correct. I'm just saying. So you see what I mean, right? So if I'm stay here, after I'm sending 1, 1, I know that I cannot be something. I can only be 1, 0. It can only be 1, 0, 0, 1. So this kind of restriction helps you to kind of do the collection. So precisely how we decode that will be something like. Remember what we received is something like this corrupted x1 or corrupted x2, x3, right? So for example, in this example here, x1, as we said, is 1, 1. That means that we are going to this here. So we are transmitting this 1, 1 here. Now, if I receive something like somewhere here, then I would expect that I have a high probability, maybe, I don't know, or actually I can even give it precisely. Let's say the noise is just Gaussian. Right? Let's just put the noise to be Gaussian. Is just with, let's say this also like this is all just equal to 1, let's say. And then let's say the noise is just Gaussian with as also variance is just equal to 1. So now if I am here, let's say if I receive something here, then I can find the likelihood function of that, right? So what I mean is that if I receive, let's say, this is 0.5 minus 0.5 minus 0.5, then I can find the likelihood function of probability that I will get x1, given that what I transmitted is or the x1 hat let's say this is equal to x1 hat. Given that what I transmitted, x1 is equal to 1, 1. So that one will be something like just kind of exponential minus that distance here, right, over 2. That distance here will be just equal to 0.5. This distance is what? I don't know what's this number. I shouldn't make. Yeah, make it complicated. Yeah.
Maybe you can use 0.3 and 0.4.
Yeah, I guess it doesn't matter because you see my point already. So anyway, this will give you the probability of 1 over 2 pi e by that thing. Yeah, that's the probability. Then I can also find this probability by x1 hat given x1 equal to 0, 1, the likelihood of all this. So now if I have likelihood of all this, then what I would be interested is that I want to maximize the likelihood. So I know that the total likelihood will be just equal to the multiple of the likelihood. This multiplied by this, multiplied by this, and multiplied by this, and so on. For example, if I have, let's say, if I think that eventually what has been transmitted is going along this path here, then the likelihood will be what I just said, the x1 hat here, multiplied by this one, basically px2 hat given x2 equal to, this is like 1, 0, multiplied by this one is probably, I don't know why is that, but x3 hat given x3 equal, I don't know, 1, 0 or 0, 1, multiplied by x4, something like that. Is, yeah. P3, there's no P for it. P x4. x4 hat given x4 equal to, this probably is 0, 0. And so of course, instead of dealing with this likelihood, I can easily deal with the log likelihood. So I just take the log of this. So, and then I flip the sign of that. So instead of trying to maximize the log likelihood, I can minimize the minus log likelihood. So then now, in the sense, I can assign the distance or the length of all this path, all this edge here. So I just transform this problem into a minimum path, like a problem of trying to find the minimum path. So of course I do try to find minimum path. Actually, from example that last time is like we can do a dynamic programming. That's people call it Entropy algorithm. Then basically you just like you know that you basically want to find the minimum path from here to here. Let's say this is the end. Then that would be the same as solving some problem of like what's the minimum path of going from here to here and here to here, because they have to go through this two. And then like kind of like iteratively go back. Eventually start with trying this trivial problem of like what's the minimum path from here to here to here, here to here, here to here, here, and so on. if you need more about dynamic programming, we can talk about it later. But what I mean, okay, this is TCM actually. We haven't go to the TCQ yet. But the TCQ is basically very much related in the sense we are using the same Trellis here, but we are not. Now we have a problem that is trying to quantize the source instead of like trying to add redundancy. Let's see, very messy here. So maybe I can so move here. So let's see how we can do that. So keep the same Trellis here. So the idea of TCQ is like this. So you see in the TCM, basically what we're doing is we kind of make your each component kind of related, and then you restrict the space. What I mean is like without this restriction from the Trellis, if I think of a so this is on in this. So okay, this is one time, this is another time, this is another time. What is okay? I guess it's going to be hard to see what I'm doing. Okay, what I want to say is like, okay, I without what we put in this restriction, it can be like, as I said, it can be like 0, 0, I can have like, after that I can have 0, 0 again, but with this restriction I cannot. So now if I instead of having this 0, 0, 0, 1, 0, 1, 1, 0, and 1, 1 as modulation point, let's put the 0, 0, 1, 1, 0 all in one dimension here. So let's say I have this is like here 0, 0, 0, 1, 1, 0, 1, 1, let's say. And that's in one dimension. Then I have another dimension. And then I can add more dimension here. And then the fourth dimension you need to imagine yourself. So, okay, so what I mean is that this is like the stage 1, let's say, this is here. And this is like, let's say, stage 2 here. And stage 3 here, let's say. So again, like, if you think of that, like, any path in this Trellis can map to a point in this spaceway. Like, in a very large dimension, I can keep on expanding that. And then, like, let's say I just stop in 5 dimensions, but anyway, I have some path is allowed, some path is not allowed, but any path will map to a point in this 5, let's say 5-dimensional space. But at the same time, that you see that this path is not have restriction, as I said, just said, like I cannot have a point. I mean, if it won't be a lattice in the sense that like every points are allowed. It's not like, for example, in this 3 dimension, it's not like okay, it's so hard to draw. Yeah, it's not like all these points are allowed. Some of the points are not allowed because of the restriction here. So if you, okay, it's hard to imagine, but it turns out that if you map this into that high dimensional space, you will get the effect of what we want at the beginning. That's basically, you will have something, it's not kind of like cubic, but something like close to spherical. And of course, like, it's not always close to spherical, but the point is you can design this trellis, right? So if you design this trellis, you try to build this point such that these points will map to the space that is kind of spherical. That's the whole point. Now you can just try to make up a trellis so that to have points that kind of look very much like spherical, then you'll be done. So and this is one example. Like this will kind of good. And of course, like, if you want to get really gain there, like, you need to have much more states. Like people do like 256 states, for example, and you will get a lot of gain, and like actually it will sound very competitive compared with those high-dimensional lattice. And of course, like, this will be totally doable because I hope that like now you will kind of have a sense that even though I didn't talk about that, you will kind of can guess like how do I do quantization now. For example, how do I do quantization? Let's say if just 5-dimensional space here. If I have a point, what I need is I need to map that point to something to the point closest to there, right? But that is exactly what TCM did previously also. What if you think of that, what we did in, that may not be easy to imagine, but if we have a point there, let's say we have arbitrarily some point here, and of course, like, as I said, not every point will be a lattice point. Let's say this point and this point will be a lattice point here, something like that. So I need to find a point is closest, lattice point is closest to this. And when I say this lattice point is the point, there's a path in this trellis. So what I can do is do the same thing. Let's say I have a point here. I will just look into each dimension, and I want to find the distance is shortest, right? So what's the distance? I can let's say I don't know, that probably, I guess probably will.
So what?
Yes.
One question.
Yeah.
The point that is the path here, it's only on the, for example, axis of the dimension. And for example, if we have a 2D, the point is only over y and x. And is there any point in the, for example, between the space or not?
Repeat the question again.
We map the path here to some point.
Yeah.
These points are in over the axis of the, for example, each dimension, or it can be, for example, part of, for example, 2 dimension. All of the points are in the.
No. Actually, each of this will be 1 dimension, right? So depends on the length of your path here. Let's say if I like 5, then this will be 5 dimensions. Each path will be
Yeah.
So if you stop at 5, you can find them, but you in general can be very long. But actually this of course I have some simplification here. So I mean, in the sense in practice, people I will explain more maybe next time, but it doesn't really map to 1 point here. What they use the trellis is like they will have kind of split the original lattice space. Let's say you can think of start with, let's say again 5 dimensions, and then you have kind of regular lattice space here. So I mean, in each dimension it's just uniformly spaced. So you have like high per dimension lattice, regular lattice, and let's say for each dimension, instead I have 4 points, I can have 8 points or 16 points. And in that case, I will just, instead of each of these represented point, I will represent a set of points instead. So that, for example, if I have 8 points, I can have like 0, 0, okay, let's say just draw one dimension here. So if I have 8 points, so let's say this 8 points here, I can have 0, 0, let's say represent this here. This is 0, 0. This represents these 2 points here. And then maybe 0, 1 is representing these 2 points here. I guess this is actually bad. I did not this way. 0, 0 should represent this and yeah, these 2 points here. And 0, 1, and then maybe this is 1, 0. Oh, I draw one more point. Oh, okay, so it's 1. Of course, if you have 16 points, you just have each side represent like 4 points there. Okay, I guess I will skip the decoding with that. Not encoding. So encoding here, like of course, in this quantization problem here is just the mapping. Right? I need to find a path that's best represent that input points there. But actually, it's quite easy. It's very actually maybe I can finish it now. It's really, you can imagine that, right? Let's say if the simpler case here, start with this only, I don't split into four set of points, but just each 0, 0 or something like that only represent 1 point here. Then because each path represents a point in space, right? So let's say there's a point in space is let's say this path here. So what's the distance of this from this? In Euclidean space, it will be like the square distance of each dimension, right? Sum of square distance of each dimension. So that's exactly right? So then I can split it into, let's say, I have this point is, let's say, I don't know, let's say 5 dimension here we're considering. That point will correspond to some, this one, x1, x2, x3, x4, x5 there. Right? Remember this is 5 dimensions, so we have 5 components here. And this point here can be like, let me just write x1 hat, x2 hat, x3 hat, x4 hat, x5 hat here. So the distance between these 2 points will be like x1 minus x1 hat square plus x2 minus 2 hat square, and so on. Of course, I need to take the square root later on. But the problem is, the point is I don't need to care about the square root. I only care about the square sum distance. So I can find the sum square distance along each trellis here, right? Because, okay, my input is basically x1, x2, x3, x4, x5 here. Now I just look at each dimension here, like 0, 0, let's say. So 0, 0, let's say this point, let's say, turns out to be 1, 1 in this dimension, let's say x1 hat here is 1, 1. So I just need to find the distance here, and now I will put this distance at the length here, right? Because now then, if I find the minimum length here is correspond to the square distance here, will be correspond to the minimum sum square distance there. And that will exactly give you the solution. that's basically. Of course, like if you have a point represent sets of points, then what you do is you just say like which one is closer. You will pick the one that's closer, right? So, for example, if there's 2 points here, then I will say I will pick the square distance of this point here and put it as the weight here. And then after you assign all the weights here, you just run through the Entropy, and then you find the shortest path, and that will correspond to your point here, and then that And by the way, like what will be the output here? So after quantization, the output originally you will have let's say each dimension is 4 points here, like 4 intervals here. I mean, for the case without splitting, like each point representing a set of points, just 1 point here. Then originally, if I don't have this Trellis thing, that would be like 4 to the 5, like if I consider 5 dimensions here. But because of this Trellis, I have the restriction that like actually along each from one stage to another stage, I only need 1 bit of information. I only need to know whether it's going up, upper path or lower path. So therefore, like you will only need 2 to 5 points here. So basically, the output here would be something like this here, like actually reduce the for each dimension, it will reduce the number of bits by 1, basically. So I guess I will kind of like, I'll try to talk about like how to find the granular gain of this thing here. The granular gain is like basically, as we mentioned earlier, that by shaping your whatever the region of each of the code word to make it more spherical, you expect that you will decrease the mean square error. And how you for different shape, then you will get a different gain, and people call this a granular gain. And I guess I probably will try to talk about like how to find the granular gain for the transcoded conversation. So okay, I guess it's quite a bit messy.